Good afternoon, Professor Cavagnero. This is Seth Stewart. I'm making my video for my Pythagorean theorem proof. And so the proof I chose today, kind of outlined it on these note cards, is one that utilizes four basic triangles. And so each of these are right triangles, with this being the right angle. And then the three sides labeled A, B, and C, kind of very similar to the Pythagorean theorem in terms of names and like sides calling. So I have these four triangles, and each of them are rotated 90 degrees and display just the same triangle in different perspectives. So what this proof utilizes is another square that has these same triangles of the different perspectives, but each of them are outlined into this square. So these are all four of these exact same triangles in this same square, using the same sides and the same measurements, the same 90-degree angles, as you can see outlined in this one, the same ones here. So now I'll talk more about this one. So this square right here uses, it obviously has the side being C of this smaller triangle, the inside having A, and then B being the short side of the right triangle. So more along this, what this does is this square right here, there's a much larger square and then there's an empty square in the middle. And so what we're going to do to prove the Pythagorean theorem and show the relationship between A, B, and C squared, each of those squared, is to find the area of this perfect square and analyze that. And so what I've done is, as you can see, this is side A, this is length A, like the other one, and then this one is B right over here, and then this is C along this side. Sorry, my perspectives are a little confusing here. But you can see that I've also listed the 90-degree angles that are also in this. So each of these make a 90-degree angle, and that helps to prove that this is a square by the fact that this is a straight line, because this is a 90-degree angle made here, and this is also a 90-degree angle made here, which makes this a 180. And I didn't draw it in, but you can see these would all be 90-degree angles as well. Should be labeled. But that makes this a straight line. That makes this a straight line, this a straight line, and this a straight line of 180 degrees. And so that proves that this in the middle right here is a perfect square. So in order, if I were to find the area of this smaller inside square, it would be length A minus length B, which that would be half of this one since all of these intersect, length A minus length B squared. And so I've predeterminedly outlined that right here. So the area of the center square is A minus B squared, and that'll find the area of the middle one. Well, for each of those triangles, those are each 1/2 A times B, which is just the basic formula for a triangle. Well, in order to find the entire area of this square, there's four triangles, so I kind of outlined my formulas here. So the area of the rest of the square is going to be 4 times AB divided by 2, which is 1/2 AB, since there's four triangles. Well, that equation simplifies to just 2AB. So with that being said, in order to find the entire square, so because we have four triangles and a center square, so that is A minus B squared plus 2AB, which is listed on this one. So what I've done is went ahead and did the math. So, another thing is that the area for the entire square should technically speaking be C squared. So it's length C times length C. So all of the math inside of here, the 2AB plus A minus B squared, should equal C squared. So I've outlined that in this. So C squared should equal A minus B squared plus 2AB. So what I've done is went ahead and simplified. So I FOILed out the A minus B squared into this equation right here, left the 2AB, carried it down, and crossed out. The 2AB cancels each other out because they're positive and negative, and that leaves you only with A squared and B squared, and the last product is C squared plus C squared equals A squared plus B squared, which is the Pythagorean theorem. And just to reiterate, the way that works out is that when you look at the relation between all these right angles and all these right triangles, you can see that the A and the B, when you find the area of the inside of this separately using strictly right triangles, which is the relationship that the Pythagorean theorem uses, when you find the area using the inside, using the square, using all these different right triangles, it directly correlates with the length of C squared, which, going back to the beginning, all the way back to the beginning, side C is the outside of this. So these triangles relate to each other. So showing the difference and showing the similarities proves the similarity between the fact that c squared is equal to a squared plus b squared. So hope that helps prove it. Hope you're having an awesome day, and I really enjoyed Wired and loved your class, enjoyed learning a whole lot about it, and hope to see you around. Thank you.